gentlemen, for your edification, witness a bug being squashed. A Tesla coil fanatic.
Yeah. Are you saying one rod is hooked on a chain? Got those 3 chains that got the 4 chains that come down? Yeah. One of the rods is up on the chain. One of the rods is up through the chain. Cycle back up. You're kidding.
He got this far and he wants to take it back up, and I said, you're kidding.
You get out of there? I love it when a plane comes together.
And yes, I did get out of there. I must tell you folks, I'm not particularly proud of this piece of video, but it does show the extents that a Tesla coil fanatic can go through. I had to maintain that position for approximately 5 minutes until the crane operator got the crane reconfigured so I could be picked up. It seemed like 5 hours. In other words, if you're going to build a big coil like this is how not to set it up.
So far, Chief. Now you got that grab, whatever shape you want to get rid of. Okay? You can't let it hang on the side because it's going to push you. Well, okay. You won't cook the straps, all right? Nylon? We'll cook the straps close to the side. Okay. Just throw it up in there. Don't bring it later. Yeah. Yeah, good idea. All right.
This is also how not to line the secondary coil. Let's spool a wire when full weighed about 380 pounds. Line it with 30 turns of maybe full wire that would round out the coil frame. What we did at Penrose Stadium, which made a lot of sense, is that when the crane picked up the framework with what's called a headed bar, that's where the hook is on the end of the crane line, it has a swivel. So we just rotated it like a carousel and wound the winder in place. No fuss, no muss. And since this was the first trial setup of Model 13M, the noise that you're hearing is from 2 300 kilowatt diesel alternators that are part of the KRLA emergency generating plant. The chief engineer elected to take the AM radio station off Edison power, off of mainline power, and run it strictly on the generators. Because we didn't know if I would interfere with the broadcasting of the AM transmitter or not.
We have to plug outside. Yeah.
The original step-down transformer, which is Cannon right, was a 3-phase transformer. We were using a single leg of it. It was only rated at 50 kVA. And the original high-voltage transformer, as I mentioned in my previous paper, was only 25 kVA, stepping up to about 30 kilovolts.
What do you got?
There's the power supply and the original high voltage power supply transformer. Here's the transmission line before it's hooked up, the primary and the secondary coil. The extra coil in the background. This setup process took approximately 6 hours, and a crew of more than 6 people to accomplish this. The original capacitor bank, The rotary spark gap. Replete with the Tesla Coil Builders Association label, emblem. That was the pressure gauge to indicate air or nitrogen pressure in the tank, because this again was in the original design of the rotary gap before making a forced air blown for cooling. There's Scott K86UDZ trying to put the final turn on top of the secondary. Stainless steel hose clamps at right angles to the Armstrong number 4 insulators is how the tubing is held in place, and simply cinch down with a nut plug. The heads of the hose clamps are turned inward so that there's no further leakage off the sharp points. That's Richard Silvera, the assistant chief engineer at the transmitter site.
Excited?
I believe it was his wife that shot this video, so you'll understand the favoritism of certain shots. There's the transmission line going across. BBC support. Some of the gentlemen there from Rosen's Electrical Equipment Company came out to witness the inaugural test firing. Here's the rotary gap being spun up for the first time. One thing I was very intent on doing was not hitting this with full power, key down, first shot out of the box. So I was raising the voltage up from 0 until I started getting breakdown across the rotary gap, and then trying to sneak up on having the right current setting and the right voltage setting to make the whole system resonate properly. And I don't mind telling you, ladies and gentlemen, I was one very nervous person. There's the bottle of pressurized nitrogen, but it was not being used during this test. Notice the strobing between the two 90-degree opposing stationary electrodes by the rotary elements. Excuse me? Oh, no, in the foreground? No, that's just a tarp or a pallet that's leaning up against the wall on the fore side. Notice the current meter there on the right. It's only showing about 250 amps. And what you heard was a breakdown across the safety gap of the capacitor bank. You can see the two black turns of the primary. This was the best that the coil was capable of performing with 25 kilowatts input power. All of this footage was taken one night before taking this whole thing apart the very next morning and putting it in a 51-foot cargo container and shipping it here to Colorado Springs in 1994. Now in this attempt, what I did was I put a metal rod on top of the toroid to act as a corona point to concentrate the discharge. Not that significant of an output, but at least it was a proof of performance test. And I believed that along with the arrival of the 100,000-watt transformer, along with my equipment from California for the symposium and the electrical show that was to take place in 1994, that I would have been successful in achieving much greater performance with this video show. And in fact, we did. Although I don't have any videos to show of it, at 2 a.m. in the morning on July 23rd, as opposed to July 22nd, which is what I thought that Saturday was. After we had a catastrophic failure of the rotary gap, which I talked about in my paper, which was a Murphy's Law problem, we did make repairs, and I did obtain discharges up to about 35, close to 40 feet a month at Penrose Stadium at 2 a.m. in the morning. The only trouble is there was nobody there except the workers to see it. So when we closed down for the night, because we've been there since 7 a.m. the previous day, non-stop, and decided to make repairs on the rotary gap in the morning, then the storm came up. So we were never permitted an opportunity to see if it would work with pressurized nitrogen in the spark gap chamber and the 100,000-watt transformer in this high altitude setting here in Colorado Springs. Again, this is all very early footage. As you're watching this, and as I look out on the audience, show of hands, who was not here for the first presentation from 7 to 8 p.m.? A couple of people, okay. For the engineer in the back, if you're capable of hearing me, what I'd like to do following this tape is let's go back to tape number 1, which shows the footage of the coil working as it has worked most recently during 1995 for the audience, so that they'll have a chance to see that very quickly. Well, we could go ahead and stop this videotape and switch to the other tape if we can. Yeah, go ahead and stop this one. Let's put tape number 1 back in, the first one. This would be tape number 1 that we're looking for. And I believe that you said you'd left it wound tails out, so you might need to rewind it. Now there's a good question, and let me give you a good answer. As big as the neighbors will tolerate. Now in my case, if you were around in 1992 and attended the International Tesla Society Symposium there, we had the first All-American Electric Show associated with the symposium at Cheyenne Mountain High School. Were you a part of that? That was with a half-wavelength resonant Tesla coil system that I had built, which has subsequently been sent to Hiroshima, Japan. All right, here's the later footage. I'll answer your question in full in a minute. Here again is stepping up into full power operation from a cautious partial power initially. You see a small corona point I'd placed on top to initiate discharge there. Actually, it's not a point. It's like the curvature of half of an eggshell.
Probably about. Are you catching a weight for it? What? Are you catching a weight for it? Same thing as that. Just all spiked there.
There's the Hewlett-Packard spectrum analyzer. Notice the amount of current that's being drawn on the load side of the circuit, over 400 amps. Okay, we can stop that tape now. Now, to answer the rest of your question, sir, let me say this, that that coil system that I made reference to from 1992 was designed and constructed and tested in my backyard where I used to live. Notice that the operative word is used to live. The original set of neighbors that I had would take out their folding chairs and sit in the backyard and watch it like a 4th of July fireworks display. And they would applaud and cheer, and they'd get out their barbecue and have a great old time. But that's the neighborhood as it was back in 1979, 1980. Then they sold the property and new people moved in, and they had a different attitude. And these people would not even tell me that they were upset or that they did not care for or like what I was doing. No, they'd let their fingers do the dialing on the telephone, call up the LA County Sheriff's Department and say, "This is an anonymous caller and I want to lodge a disturbing the peace complaint." Next thing you know, you got the cops at your door. And what do they know about all of this? What are they to make out of it? They haven't the foggiest. So it became a serious problem. I was very grateful to have the opportunity to move to an industrial site in what is zoned as industrial property, where nobody could tell me what I could or couldn't do as far as making arcs and sparks are concerned. That's a luxury that very few Tesla coil builders have. I have a friend who built a coil, made an arc about 4 foot long, and a neighbor who lived in an apartment, because his area where he lives in Hawthorne is zone R1, R2, and R3, all within less than a half a block. Didn't even bother to call the police. He got out his 30-06 and started shooting at it. So how big of a Tesla coil can you build in your backyard? As big as you can get away with, that the neighbors will allow. That's the answer to your question. The answer to your question about what size spark and what reading reference to use as a guide, there's quite a number of them. I can't say right now at this time here at this podium any one reference, but there are a number of excellent references that are in the bookstore right across the hallway that you should check out. I would say there's at least a half a dozen. And where they have an open copy that you can look at and thumb through, you'll see for yourself what looks like it's valid reading for coil construction. On a very small scale, yes, because if you go back to a publication called Popular Electronics magazine throughout the 50s and the 60s especially, and I'm reminded of an article from October of 1962 that appeared in Popular Electronics. It was called Tesla's Trickery. And it showed you how to build a very small Tesla coil. It had a photo that the credit was given of the Bateman archive, but in actuality it was one of Tesla's photos from his lecture and his article for Century magazine entitled The Problem of Increasing Human Energy. So it shows the extra coil striking an unconnected resonant coil some 22 feet away in the Colorado Springs facility here. And the coil project is built on a breadboard, 8.5 by 12, using a Model T Ford ignition coil for a power source and a 6-volt battery. You make your own capacitor out of a single sheet of glass, 1/16 thick, 4 by 5. You wind the secondary of a Tesla coil that's 3/4 of an inch in diameter, 3 inches tall, with about 2.5 inches tightly spaced wound of number 36 gauge form var wire, which is about the same thickness as a human hair. And then you use a couple of turns of number 18 wire for primary, and you make a spark gap fashioned out of a couple of copper wires. I built that project, and I was able to make a spark almost a half-inch long off of the secondary coil. Yeah. Okay. So that's the answer to your question. There's lots of construction articles. I know one book that comes to mind very briefly is Curtis's book, Stanley Curtis, that is available in the bookstore, because the coil construction techniques there are using common materials that are readily available. And it's a historic reference. It's not that modern and up-to-date, but it has a lot of good information in it. And I'm being told from the side here that I need to kind of wrap this up here pretty quick. Let's bring up the house slides, please, because I'd like to take some more questions from the audience if anyone has. I see some hands raised. You, sir, please. That's Harry Goldman, TCBA, Queensbury, New York. Right. And he's doing an outstanding job. And by the way, sir, also to answer your question, that is an excellent source of information, because you're talking about people who are interested in building Tesla coils, from a first-time builder to someone who's built maybe a dozen or more coils. And the articles are featured in that publication. It's very worthwhile reading. It's called Tesla Coil Builders Association, or TCBA News. And I'm sure you can get that information through the society as to how to get a hold of Harry Goldman here. Any more questions? Sir, yes. All right, the question is, what is a practical application for a Tesla coil? I love questions like that. Well, here sits a little TV monitor. This produces what is called an NTSC composite video image. It's like your picture tube and your TV set at home. It's like your monitor for your computer. What do you suppose produces the high voltage that accelerates the electrons that strikes the surface of the CRT, or the cathode ray tube? A hybrid version of a Tesla coil. It is a radio frequency resonant transformer. True, it uses a ferrite core, but it operates as a high frequency step-up transformer. So it's an outgrowth, or a hybrid, a cousin of a true Tesla coil. Ever see an arc welder that does heliarc welding? Do you know what the heliarc process is all about? They have what's called a kickbox. It's a high-frequency generator, a spark gap-driven Tesla coil that superimposes high-frequency electricity on top of high-current, low-voltage DC or AC that generates the original plasma arc, along with argon gas, which is the inert gas that makes it TIG welding, tungsten inert gas welding. That's an industrial application of a Tesla coil. There's many more. Sir, yeah, we've got to go quickly. Okay, last question. I'm sorry. I'm sorry, I didn't hear the question. The papers that I made reference to. You mean about the breakdown of high-frequency electricity? Oh, you mean, okay. Spark gap technology. Yeah, that comes through the International Tesla Society. They have those. Right. Well, I don't know that they have them at the bookstore right now, but yeah, that full series is available on videotape, as well as I think it should be also available in print. I can't say that they will or they will not, but they have been available in the past. Yes. Is there any last question? I know we're running real short on time. One. Question is where's Model 13M at now? Ironically, it's in an airport hangar in El Monte, California. It's in storage. It's built like a giant erector set, so it breaks down into simple pieces that are more easily transportable, and it's in storage. I couldn't leave it up through the rainy season anticipated for 95 to 96. Needless to say, we didn't have a rainy season this year. So I could have left it set up, and I do plan to set it up again, and I detail future efforts for the continuing evolution and development of that system, hopefully in a more quiet RF environment than in the near field of a 50,000 watt AM transmitter site. With all of its advantages, I cannot do any characteristic measurements of impedance or capacitance because the RF field is too intense. I just can't do it. All I can do is just calculated estimations. Thank you, ladies and gentlemen.